the topic of synchronous machining continues, and this example is actually linked with the previous example that we have solved. And in this example we had a machine, synchronous motor, and what we did was we changed the output load for the machine from once we calculated for 15 horsepower, then we calculated for 30 horsepower. The excitation remained the same, therefore in the output what we saw that the internally generated voltage EA was the same, but the output power changed. And for this machine, for 15 horsepower load, we have also calculated the input power for the machine, and by the basis of this input power we were able to calculate the armature current for the machine, that was 27.4 for this case. Now here what has changed is the power for this machine. The power factor has changed, 0.85 power factor lagging, and what is required in part A is we are required to calculate the initial phasor diagram of the motor and calculate the per phase values of EA and IA. So for the machine that this is V terminal, this is EA, this is X of S, that is 2.5 ohms, and this is IFA. So first of all, we know that the value of P input for our machine that we calculated in the example 6-1 was 13.69 kilowatt. Now we can calculate this is the total power, and we know that this machine is delta connected. So for any three-phase machine, the three-phase power can also be calculated by the formula Pn is equals to 3 times V terminal or V phase into I phase, that is for our case it is IA cos of theta, which in our case is 0.85. So the value of Vt is 208 volts, that is given, and input power we know. So the value of IA we can calculate from these values, and it will become 25.8 amperes with an angle of minus 31.8 degrees. This is the current IA. And when we have this current, can we calculate EA? Yes, by applying KVL to this formula. EA is equals to Vt minus IA J X of S. So for our case this is 208 volts with angle 0 minus what is IA, 25.8 with angle minus 31.8 into 2.5 ohms with angle 90 degrees, where this is X of S. This is 2.5 ohms, and the value for E of A would become 182 volts and with the angle of minus 17.5 degrees. And so if you want to draw the phasor now, the phasor diagram for this will become, this is Vt, and what about our current? Our current was, this is Ia, and the angle is minus 31.8, that is the power factor was lagging. So to draw this part for the vectors, this will become minus A Jx of S, and this will then be converted into this value. This will be like this, and the internally generated voltage EA will be like this. Sorry, this is actually like this. This is minus IA Jx of S, and this is actually EA for our given value. Now what happens is, what they have done, So this was the phasor, and then let's look at what's required in part B. And if the motor's flux is increased by 25%, sketch the new phasor diagram of the motor and calculate these values. Now we know that when we increase the flux by 25%, so, and we know that let's make it like this, the flux is increased by 25%, and we know that EA is equals to K phi omega. So what will happen will be the internally generated voltage for part B will increase, so we can call it EA2, that is the internally generated voltage is actually 1.25 into EA1. So this was actually, I will call it EA1 for the first scenario. And now when we have changed the field current, it has increased, and this value will become EA2 is equals to 2, let's make it 227.5 volts. So now this value has changed. Now what else would change for both the scenarios and for both the machine? Now let's consider this as the load has remained the same on the motor. Okay, so the P output is same, so the P input is also same. The input power, real power, and the output real power is same. But what has changed is actually the voltage that is being generated inside the machine, that is EA, but because we have changed this IF. So we can say that the power that was being drawn for the case 1, that was P case 1 is actually equals to P case 2. So the power that was being transferred or being converted by the machine for the case 1 was actually 3 V terminal EA1 over X of S into sine delta 1 was actually equals to 3. The terminal voltage remains same, the internally generated voltage has changed, the power factor angle will be changed, and the synchronous reactance remains the same. So if these are all the same, so this is actually the equation. So we can calculate the power angle for the part B in which flux was changed. Delta 2 can be calculated. Delta 1 we know. What is delta 1? Delta 1 is minus 17.5, and EA1 we also know. So the value of delta 2 would be minus 13.9 degrees. This will be the new value. And now if the delta 2 has changed, the current that is being drawn by the machine will also change. Which current? This current IA. This current has also changed. So what will happen for this scenario will be, we are again applying KVL to this and calculating the value of IA, because we know, let's draw this again. Now for the part 2, there is a voltage EA2 generated. Here VT is the same, this is the current IA, this is X of S. So the interesting phenomena will be the value of IA2 by the KVL will become VT minus EA2 over J X of S. VT we know is 208 with angle 0 degrees, and EA2 is actually the voltage that we find 227.5, and with the angle delta 2. And so the value of IA2, by solving this, we can calculate this value, and it will become 22.5 with angle 13.2. So what happened here, we can see, is that the current is now leading the voltage. What was happening in this scenario? The current was lagging the voltage for part A, but as we change the excitation of our synchronous machine, we have converted our machine from a lagging power factor to a leading power factor, and now this current is leading the voltage Vt. So it will be actually supplying the reactive power and not consuming the reactive power. And the new power factor for the machine, we can see this is 13.2, the angle between the terminal voltage and the current, and this will become cos 13.2, and this is actually 0.974 leading. This will be the power factor. And now if you want to draw this diagram, and let's draw this in another color. For the green will be the color, so the again Vt remains the same, but what has happened is there is IA2. It is, the current is now leading the voltage, and minus, and when we draw this from the KVL, what will happen with, here is the current vector, and the new voltage EA2 will be actually like this. This will be EA2. This was EA1. So this is actually EA2, and this is how the machine will be providing the power to that thing. So I hope it helps. I think it is clear now that what are the effects of changing the excitation and what can be the effects of changing the load on the motor. Thank you.